Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 26, 2026, about 5 days ago. It introduces a framework called SP3F that enables a model to outperform a strong baseline on multilingual reasoning tasks, even while using less than 1/8 of the training data. The paper is titled, Gained in Translation, Privileged Pairwise Judges Enhance Multilingual Reasoning. And as we'll see later, the method achieves striking improvements for low-resource languages like Swahili. Alright, Figure 1 illustrates this efficiency gap right away. The chart plots performance on two axes. Language fidelity on the x-axis, which measures if the model responds in the correct target language, and accuracy on the y-axis. Starting at the bottom left, we see the base model, QN2.57b. The purple arrow tracks the standard instruct version, trained on 1 million samples, which achieves solid results. However, look at the orange path, specifically the top right point labeled SP3F7b. This model outperforms the instruct baseline on both metrics, yet it uses only 125,000 samples, roughly 1/8 of the data. So, having seen the performance gains, Figure 2 breaks down the reinforcement learning stage that makes them possible. First, on the left, the model samples multiple candidate responses, labeled 1 through n, for a given prompt. Then, in the center, these responses face off in pairwise comparisons. The key innovation here is the privileged judge, which accesses the correct English reference to accurately pick the winner, even for languages it barely knows. Finally, on the right, the method calculates a win rate for each response, using that score as the reward signal for training. Well, Table 1 details the quantitative performance across these benchmarks. If we focus on the overall accuracy column, the proposed SP3F7b model reaches nearly 62%. This score notably surpasses the strong QN2.57b instruct baseline in the bottom block, which sits at roughly 56%. The gains are especially clear in math benchmarks like MGSM, where the method jumps to 72% accuracy. Comparing this to the plus RLVR row helps isolate the impact of the judge. Adding the privileged feedback yields consistently better results than verifiable rewards alone. Okay. While Table 1 gave the global average, Figure 3 splits the results by language, ordered from low resource on the left to high resource on the right. In the Swahili panel, notice that the standard instruct model, marked by the purple dot, barely reaches 5% accuracy. However, the orange point for SP3F shoots up to roughly 35%, effectively tripling the baseline performance. The arrows connect the training stages, showing how the model progresses from the gray base, through blue fine-tuning, to the final orange reinforced state. Even in the Spanish panel on the far right, where data is plentiful, the method still secures the top spot. Alright, Figure 3 covered the languages included in training. Now Table 2 asks a harder question. How does the model handle languages it never saw before? This table compares performance on 8 unseen languages across the Belabele and MT Math 100 benchmarks. The average row immediately highlights the gain. On the left side for Belabele, accuracy jumps from roughly 40% with the baseline to over 58% with SP3F. Furthermore, look at the language fidelity columns labeled lang. While the baseline often fails to reply in the correct language, averaging just 63% on the math task, the new model achieves near-perfect consistency, proving that the method's benefits generalize even to zero-shot settings. So, Figure 4 offers a different perspective by plotting the improvement over the base model, rather than raw scores. Here, the orange bars represent the SP3F model, while the purple bars show the standard instruct baseline. In the top average row, the orange bars consistently extend further to the right, indicating a larger performance boost across all 4 benchmarks. The difference is stark in the third column for the Belabele task. Scan down to the Hindi row, labeled HI, where the purple bar shows a modest 7-point gain, but the orange bar surges to over 32 points, highlighting the method's strength in lower resource settings. Well, Figure 4 demonstrated the overall framework's power, but Table 4 now isolates the specific contribution of the privileged judge. Here, the rows compare models trained with the privileged judge, labeled P-Priv, against those trained with the standard non-privileged judge, P-No-Priv. Looking at the average column, the privileged approach scores 64.6%, beating the non-privileged version by over a point. The difference is most pronounced in the math section. For instance, on MT Math 100, the score improves from 53.6 to 56.8%, confirming that giving the judge the English reference leads to better training outcomes. Wrapping up, 2 main takeaways stand out. High-quality multilingual reasoning does not require massive native datasets, and giving judges privileged access to English answers efficiently bridges the performance gap. This framework matches larger models with just 1/8 of the data, offering a vital solution for underrepresented languages. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.